Thanks for the introduction, Manveer. I'm Johannes, one of the co-founders of Prime Intellect, and I'm going to take a few moments to talk a bit about the existing research we've been doing in Decentralized AI before Sami and Justus are going to kick it off with what's coming next. So I'm going to touch on everything from decentralized training to building models in high-impact domains like science, to synthetic data generation, which we've been doing, as well as verifiable compute. And let's kick it off with decentralized training, which Dylan Patel already touched on, and showed that all the big labs are currently looking into how to train across their different clusters of compute. But especially for the open source community, it would be great if we can pool all the resources, utilize all the idle compute resources in the world to train a foundation model together. And we started out at the beginning of last year, reproduced some work by Google DeepMind called DiLoco, distributed low communication training, successfully reproduced that and scaled it to the 1 billion parameter size. And then, later that year, we did a public run where everybody was able to contribute resources to our Intellect run and train the first 10 billion parameter model in a decentralized setting. And on this map, you can see all the extremely based compute contributors from our last run that provided compute resources to it. And to give you guys a bit more stats on the training run, we were training across 3 different continents at the same time, 5 countries. We utilized over 100 GPUs simultaneously in the run. We were very competitive to like a centralized training setting and achieving 92-98% utilization compared to a centralized setting. We trained in this test run on 1 trillion tokens, and it's all built on our open source decentralized training framework called Prime, which enables this fault-tolerant training in PyTorch and a bunch of other features needed to make this globally distributed training work. And we've been building on top of for our next one as well in the open source. And we won't stop here. We will scale this to even further, larger model sizes, more compute nodes that could join the training run, as well as training on more tokens to be competitive, as well as bring the whole decentralized training aspect to this new paradigm of test time compute that Sami is going to tell you guys more about later. But beyond just training like state-of-the-art models in language as well as reasoning, from the beginning, we've been interested also to train foundation models collaboratively for other domains or high-impact domains like science. We had our first collaboration here with MetaGene1, which is a metagenomic foundation model for pandemic monitoring, which we trained in collaboration with the USC and the Nucleic Acid Observatory. And it's a 7 billion parameter model. We trained it on 1.5 trillion DNA and RNA base pairs of sequenced wastewater samples. And it's one of the most beautiful examples, in my opinion, on how much potential impact you can have per flop of compute. So this particular model only cost us around $20,000 to $30,000 of compute, and we achieved state-of-the-art results for different benchmarks across genomic embedding benchmarks as well as pathogen detection. So how far your compute can go there as well, compared to how much money is wasted on large language model training runs. And we're interested to explore scaling that further, train it on even bigger models, more tokens, as well as doing any kinds of other collaboration on the scientific foundation model front. So if anybody is interested there, reach out to us. Beyond scientific foundation models, one of the things we've been really excited about over the last couple of months has been synthetic data generation, especially with all the powerful models coming out. For one side, the Llama series, obviously, that we're going to hear about later more, as well as all the DeepSeek models with the B3 model and the R1 reasoning model in particular. One of the interesting things is to use those models to generate verified reasoning traces for domains like math and coding, and self-improve those systems on its own outputs. So right when the DeepSeek R1 model came out, we took it for a spin and collaboratively generated Synthetic 1, which is the largest open source reasoning data set based on R1. So everybody was, again, able to contribute their resources to generate this data set of 2 million verified reasoning traces across math, coding, and science. So we have different tasks and verifiers here, from verifiable math to coding problems with unit tests, as well as STEM questions and so on. And with this release, we also released an open source library called Genesis, which is our framework and effort to crowdsource different tasks and verifiers to actually crowdsource this part of the stack to generate more reasoning data, as well as for the reinforcement learning paradigm. So we're very interested to advance that further, and I think that's one of the things where open source can really outcompete the closed labs in terms of crowdsourcing all of this. And last but not least, on the work we've done so far, is on the verifiable compute component. Everything I've shown so far with people contributing GPU resources is only possible if you actually want to do it in a permissionless way that everybody can contribute to those training runs. And one of the components we have to solve for this is how can we actually detect if somebody is doing malicious behavior, if they're actually the hosting model that they are supposed to host. So one of our earlier works there is TopLock, which is a locative sensitive hashing scheme, which provides a proof of an inference computation in a very efficient way. It's robust. If you, for example, would use a different model, it could detect that. If you use a different model prompt, we could detect that, as well as if you use a different precision. So we can make sure that somebody is running the FP16 precision model and not like some quantized version. It's also resilient across hardware non-determinism. So one of the challenges is always with verifiable computing that your GPU operations are usually non-deterministic. So in this case, we've also have something that's resilient across like different GPU types, as well as different tensor parallel configuration and stuff like this. And it's very efficient to verify. So the verification is a lot more efficient than the actual generation of the proof. And we're excited to put TopLock into production. So our next training run is going to be completely permissionless. Everybody from around the world could contribute to our next run. And what we're actually going to train there and what's coming next is what Sami is actually going to tell you about.
Thanks, Johannes, for the introduction. I'm Sami. I'm leading the research here at Prime, and today I'm going to talk about what we're going to do next in terms of training decentralized model, and deep dive into Intellect 2 is going to be our next model training. But before talking about Intellect 2, let's try to understand what are the bottlenecks with decentralized training, what make it hard. There is a lot of bottlenecks, but three of them will be, the first important one is the bandwidth. Decentralized training works with really low bandwidth over the internet, which is 2 orders of magnitude slower what you can get into a centralized cluster of training. Second one is memory usage. It's kind of linked to the bandwidth, but in a decentralized setting, usually your unit of compute are smaller than what you can find, and you cannot really share as much as you can in a classical centralized data center. And more importantly is deep learning algorithm have been becoming more rigid and rigid with time, up to a point where it's very difficult to do any kind of asynchronicity. So what we look for in decentralized training research is 3 things. Anything that can increase compute density, which means that we're going to spend more time computing instead of communicating, is great for decentralized training. Any algorithms that can reduce memory usage, so basically allowing to fit bigger model on the same unit of compute, is great for decentralized training. More importantly is any algorithm which is naturally more async than the traditional deep learning algorithm is as well great for decentralized training. And when I'm talking about this is I want to introduce our next work, and we want to scale test time compute. I think most of you know what test time compute scaling is, but you have heard about DeepSeek R1, about OpenAI O1 and O3. And this is a new paradigm of scaling compute and scaling training. And the idea of test time scaling is in the pre-training era, to get better performance on a model, you increase the size. When you increase the size of the model, you increase the memory requirement and you increase the bandwidth requirement. Test time compute is a bit different. Instead of increasing the size of the model, you're going to increase the time it's going to spend at inference time to resolve a problem. So you still scale the compute, but you stay with the same memory footprint and the same model size. So in a nutshell, that's what test time compute is. And I want to argue here why it's actually bullish for decentralized training. Because first, in test time scaling, you're generating data that you train on. It means that you increase your compute density. You're spending actually time generating the data. It's inference time, and overall, you're reducing the amount of time, the frequency at which you're doing communication. Second thing is you reduce memory usage, or I should rather say that to get better performance, you can keep the memory footprint the same, making it a great case for decentralized training. Test times compute is as well very good for async algorithm, and I will explain a little bit later why, but it's naturally more async than the way we do deep learning right now. And DCL2 announcing Intellect 2 is going to be our next model training starting in the next weeks. We're going to scale up to 7 GB reasoning model on between 500 to 1,000 GPU, so almost one order of magnitude more than what we were able to do for Intellect 1. We're going to support heterogeneous compute. People are going to be able to join with multiple generations of GPU, H100, A100 from the last years. More importantly, everything is going to be fully trustless. Manvir already introduced what we mean by trustless. Is going to get more in detail, but that's our setup for Intellect 2. We're really proud to be announcing the start of the training in a couple of weeks. And let's look a bit more under the hood what's going to happen with Intellect 2. So in Intellect 2, we're going to scale async reinforcement learning to this 1,000 GPU scale. And how async reinforcement learning is working is basically there is 3 types of compute in async reinforcement learning and in reinforcement learning in general. The more important one is the rollout, the inference worker. Those are doing the hard work of collecting information from the environment that they run on. It basically see it as like some kind of model running code execution and getting reward and feedback from the environment. And yeah, it's really collecting the data. And these are the rollout worker. After this rollout worker has basically created the data that we want to train on, we are going to validate that these inference are actually doing the job that they were supposed to do. And that's where our top lock and trustless inference are coming into play. The third point, the most important point, is the training. Once we have all of this newly collected data, we're going to train on it. So that's like the cycle of reinforcement learning in general. What we're doing is going to do async reinforcement learning. It means that those 3 entities are going to always play at the same time. While the inference are collecting new data, we are training all the slightly oldest data that was collected from previous generation ago. And the idea is, in this setup, we have non-blocking. We are never waiting for communication. Actually, like the biggest communication is to update the weight of the model to the inference worker. And this is a broadcast. We're going to send the weight to all of the inference worker. And in normal centralized setting, this will be a blocking operation. But in the async reinforcement learning paradigm, this actually happened under the hood, meaning that we never saw it. We never see performance degradation. And this actually does the case for decentralized training being, in this setup, in async reinforcement learning, as competitive as a co-located cluster of training. And it actually, this is going in the right direction for us as like, well, basically in this stage, almost no bottleneck compared to the bigger labs in training model. Yeah, and I'm giving back to Justus, who are going to explain how we are going to take this test time scaling and what's our path to AGI and agent training.
All right. Yeah, thank you, Semi. Hey, everyone. I'm Justus. I'm also a research engineer here at Prime Intellect. And what I'm going to talk about is, okay, where do we go from here? If we, scale reasoning even further, and how do we go from here maybe to general intelligence that is actually useful for, automating mundane tasks, accelerating scientific progress, and everything essentially that we want an AI to do. So first of all, of course, we are going to continue, our research on pre-training and training models with larger sizes. As Manvir said, we want to be an AI lab that can compete with OpenAI and DeepSeek, and so we will also, want to have the capabilities to train, let's say, 700 billion parameter mixture of expert model. But beyond that, there's sort of a more non-obvious research direction that we're incredibly excited about, which is more in the domain of, test time compute, and that is training agents end to end. And it's always sort of been said throughout the last years that, okay, this is going to be the year where agents are actually going to take off and where they're going to be useful. But we really believe that, okay, now there's actually a good technical reason for agents to be useful. And that's what I want to talk about. So if we kind of look at how agents are kind of trained today, or how they're built today, nowadays people really use off-the-shelf models, so ChatGPT or Claude, and they just use their APIs with prompting. And they're usually set up in a very constrained rule-based workflow. So you might imagine some flowchart where a human has priors about how a certain workflow should look like. So if you have a voice agent for appointment booking, you might first want to classify the user's intent, and then give the agent tools to kind of resolve the intent, and so on, and do that all in a very structured manner. But this kind of rule-based workflow is very constraining, right? If we think about sort of the bitter lesson, it tells us that everything that can be learned should be learned, and we should give our system or our model as much freedom to choose and learn as possible, and not kind of constrain it through feature engineering based on our human priors. And with sort of us figuring out that reinforcement learning across long contexts actually works really well, this really opens up a path to actually train agents and to optimize them in a good way, rather than just have them imitate what we think a certain workflow should look like. So what we really want to do if we want to train an agent is we want to kind of remove human priors as much as possible, just give the agent as much freedom as possible to plan and use all the tools that are available, and then use reinforcement learning to train a reasoning model that can call tools and APIs and whatever throughout its reasoning chain, to solve the problem it's given. So if you have a math problem, you might imagine that you might want to give a model access to a Python interpreter to solve intermediate computations, and then take the result of that computation and continue with its reasoning chain. And we're already seeing that labs are doing that. So a very prominent example of probably the first end-to-end trained agent that is out there and that is widely available and used is deep research by OpenAI. OpenAI has confirmed that deep research is O3 with access to tool calls, which are web search and also Python interpreters and so on, to do computations. And the deep research was trained with reinforcement learning in an end-to-end manner. Now, deep research is a very, very specialized agent, right? It's only built to solve one very specific task. And it makes sense that agents are going to be built this way. So most likely the future that we're going to have is we're not going to have one model to rule them all, which is sort of what is the case right now. People are using GPT 4.5 or Claude Sonnet 3.7 for pretty much everything, and don't really use one specialized coding model, one specialized writing model, and one specialized model for writing emails or so on. But people really just use these very big general models for kind of everything that is there. But with the way we're training agents, this really shifts. And we really think that, okay, in the future, we're going to probably have hundreds or thousands of agents that are all trained for very specific tasks. And the bottleneck to train these multiple agents will probably not be the reinforcement learning algorithm you use, because it's sort of been shown that through all the papers after DeepSeek R1, the RL recipe doesn't really matter too much. You can train with PPO, you can train with GRPO, you can train with RLU or whatever reinforcement learning algorithms there are. As long as you have a good objective, a good reward function to grade the steps that the agent takes, you're going to be good, and the model is going to learn. And so the real bottleneck is more about the environments that you have to train an agent. And by environment, I mean some environment that an agent can interact with, do actions in, and receive a reward for what it does. So as an example for that, we could have kernel bench, which lets an LLM write kernel code and then execute that kernel code to get the runtime and metrics that it grades the code based on. And if you think about it, this problem of building environments is really more of a traditional software engineering problem and not too much a model training problem. And traditional software engineering, it's obvious that open source and collaborative software development is definitely the preferred way, right? All of the developers across the world can collaborate much more efficiently than one single company to train and build these hundreds of different environments that are needed to train individual models. And so really just the takeaway here is that, first of all, we need a very good open source based reasoning model that we can train to do specific tasks as an agent. And secondly, the infrastructure requirements are different than before, where we're not going to have one model that we need to serve and train, but instead we need to enable multiple smaller groups of developers with domain expertise to build environments, to fine-tune this big open source reasoning model, to then train agents and serve them to do tasks like scientific advancement or whatever we want an agent to do. And clearly, this sort of infrastructure is much better, or these infrastructure requirements are much better suited for a decentralized setup than by what a single large lab can do. And with that, I'm handing it over to Manveer, who's going to talk about how we are going to enable this infrastructure for people to collaborate and collectively build agents and intelligence. So, yeah.
Okay. So I realize you guys have probably been sitting through a lot of presentations. Trust me, this will be interesting. So this is our protocol is one piece of Prime Intellect that I think is less touched on or is less well known. We've been starting to be a lot more public about it recently. We've been talking a lot more about it recently, and I think we'll do a lot more in the future as well too. But yeah, so I'm going to introduce how we're actually thinking of building our peer-to-peer computed intelligence protocol and what this actually is as well. So I'll bring back this slide because I think it frames it in the right way. Essentially, everything that Johannes, Sami, and Eustace touched on fits within that first framing of us as an open source AGI lab. And our protocol is meant to be this point two. So open infrastructure for decentralized AI. It's meant to be the economic and technical backbone that enables decentralized AI at scale. And so what does that actually look like? You can think of this as maybe an Ethereum for AI. So there's a couple of key components to this. At the base layer, we'll have global compute and intelligence markets. So we'll aggregate global data center compute, aggregate global consumer compute. And then on top of that, we're building frameworks for decentralized training, distributed RL, essentially frameworks that can leverage this distributed compute and enable us to both train and inference open models. And thirdly, we're very excited about exploring and enabling crowdfunding and novel revenue streams for open source models on top of this infrastructure as well. And I think the key point is that all of this will be open and permissionless. We don't want to own this all as a company. We kind of want to open source it and give it as a public good, in a sense. And we want it to be permissionless so that anybody in the world can build on it. We want anybody in the world to be able to come to this protocol, to come to our protocol, and crowdfund open models, or crowdfund open data sets, and as well as just access open intelligence permissionlessly as well too. And I think it's really important for us to also add a little bit more color and substantiate why we're building a protocol in the first place. And the way that we frame it, we think of it in terms of what we think open source AI needs today. What are the qualities that we want from our open source AI ecosystem, and what are the key ingredients that we need? And we definitely need a lot of compute. Open source AI needs a lot of compute to compete with the level of scale that these superintelligence labs are building out. We also want open source AI to be genuinely sovereign. We don't want it to be dependent on some benevolent company or some benevolent state sponsoring it. We want the open source AI to actually exist fully independently. And thirdly, we want it to be permissionless. So we don't want anybody being able to tell you that you can't train a model or that you can't access and inference some open model. So we want it to be permissionless and open for anybody to access. And we see protocols as the only way to enable these sorts of attributes. Decentralized compute protocols like Bitcoin and Ethereum are kind of the canonical examples here, where they've aggregated a lot of distributed global compute and enabled the creation of open, permissionless, sovereign use cases and apps on top of them. And so that's where we sort of draw our inspiration from. And I think our Intellect 1 and Synthetic 1 training runs, as well as synthetic data generation runs, are good glimpses into the future, into this aspect, where basically anonymous individuals from around the world crowdfunded over 100,000 H100 hours of compute and over 360,000 exaflops of compute to actually build open models and open data sets. And we think our protocol can enable this at in order of magnitude more scale. And so what have we actually built so far? How far along are we on this? So for Intellect 2, we're actually going to be releasing our public testnet, where basically anybody in the world will be able to run our worker on their GPU, contribute their compute to a network, and have that compute be used for the training of our next model training run. And this will all be settled on top of Ethereum. What that basically means, I realize this diagram is quite complicated. It's in our blog post and everything. We'll post it online and everything too. But essentially, what is covered here is that all nodes that are joining the network, whether they're registering with the network, whether they're joining the compute pool, as well as their contributions, are all tracked and mediated and settled on top of Ethereum. And what that actually means is that this infrastructure exists outside of Prime Intellect to some extent. Whereas if Prime Intellect stopped being an entity tomorrow, this infrastructure would still exist, and people would still be able to leverage this infrastructure to train open models. And yeah, as Sammy touched on, people who are contributing to this Intellect 2 training run will be able to contribute inference workers to the training run, meaning that the compute that they contribute will be used on the synthetic data generation side of our infrastructure. But obviously, if you allow anybody to contribute, you also open up room for malicious actors as well, whether it's people trying to fake GPUs or even fake the data that they're submitting, or even try to poison the data sets or poison the training run and just mess with it. And so how do we actually prevent and mitigate those attacks? We essentially think of it as a multi-layered defense, where we're introducing a separate validator entity that does a number of checks on the network and ensures the integrity of the network. So whether that's actually issuing performance challenges on the nodes themselves to check whether their hardware is up to par, whether that's even just monitoring the network and monitoring heartbeats to check for anomalies, and even getting all nodes to generate proof of inference, which uses the top lock scheme that Johannes referred to before, which essentially allows us to generate very efficient proofs of the inference that was used to generate the synthetic data that's used in the training run. And we can also efficiently verify that it was legitimate as well too. And so that's kind of what we have so far with our testnet, and where is it really going from here? So Eustace touched more on the AI side, where we're obviously looking at training agents end-to-end, and we're obviously wanting to produce frontier open models with the objective of building open AGI. But then from a protocol perspective, the way that we think of it is you can currently, with our testnet, crowdfund open models, you can crowdfund open data sets, but we also want to support more use cases, like actually enabling agents to run autonomously on top of this protocol, as well as like agents that can leverage distributed compute contributions as well. And we're also very excited to open up this infrastructure in the future to enable other companies, other communities to crowdfund their models and data sets through here. And ultimately, the vision is to move towards a future where we can have a protocol that can sort of like self-upgrade with the needs of future humanity as well as with future superintelligences. And so this is to sort of like wrap up this whole Prime Intellect section of like, if you want to get involved, if you want to help out, if this is exciting to you, you can definitely like contribute compute to our next model training run. We're also hiring across like literally every team, whether it's like research, whether it's protocol engineering, whether it's even just full stack engineering and design. So if you're interested in getting involved, please reach out. And also, if you're training interesting agents, models, scientific models, coding models, or like producing interesting data sets as well, we would love to collab with you on that. But yeah, that's pretty much it from us. Definitely like reach out and like meet our team members. We're all here with the Prime Intellect shirt for like the rest of the day, as well as like later into the evening after the presentations are over. But yeah, I'll leave it at that. Thank you for your time.